The question of life on Mars is a very old one. Schiaparelli, Lowell, and science fiction fans will remember the Barsoom of Burroughs, and of course, H.G. Wells. But in all this time, as we learned more about Mars, we found out that there was no one there drawing their plans against us. Now, however, we find that at least in the distant past, and perhaps even today, Mars may have been, strongest evidence yet, alive with microbial life. I recorded this interview less than 2 hours ago, and producer Ross and audiovisual specialist Aaron bring it to you now as fast as we possibly could regarding this highly important and newly announced, as of yesterday, finding. It represents the best evidence so far of the action of biology of some sort on another world. But what would it mean if we did find evidence of past microbes on Mars? Is it a second abiogenesis? Or is it life that either originated on Mars and transferred to Earth, or vice versa? I ask you to ponder this. Did life on Earth start on Mars?
You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Stephen Benner. Stephen Benner heads the Foundation for Applied Molecular Evolution, which he founded after serving on faculty at Harvard, ETH Zurich, and the University of Florida. His research combines two traditions in science, one from natural history and the other from physical sciences. His laboratory has been a leader in the field of synthetic biology, where it has redesigned DNA to better understand how these molecules work, generate new classes of diagnostics tools, and to open new avenues to disease therapy. Separately, he also created the field of paleogenetics. His work also guides NASA missions to search for alien life and how life originated. His most recent book is titled Life, the Universe, and the Scientific Method.
Dr. Stephen Benner, welcome back to the program.
Thank you.
Now, Doctor, we have a potentially Earth-shaking or Mars-shaking discovery here that has come out and was announced by NASA yesterday in the publication of the paper regarding it. And it's in regards to a core sample taken by the Perseverance rover that it's called Sapphire Canyon. And this general rock that this came from, that it was drilled from, has been of great interest for quite some time now because they noticed what were called leopard spots and poppy seeds on it. And they're like, could that be something that was related to biology? Well, now we seem to have an indicator that it is, and it seems to be the mineral chiefly, but that's not the only thing here, but the mineral vivianite. Can you tell us what links vivianite with life?
Yeah, sure. So let me first place, as you know, geologists have this code by which they give names to rocks, minerals, and places. I kind of object to this because it's a way of keeping the layman out of it. But vivianite is a mineral. It's an iron phosphate. More importantly, it is a reduced iron phosphate. That is, it's an iron with a +2 charge in contrast to most of what the iron is that is visible on the surface of Mars, which is the reddish iron 3 plus materials. So it is reduced. We like to say in chemistry that the mineral contains reduced iron. It's iron phosphate to begin with. It has some water associated with it. So that's what they found. And the second thing they found, again, Bright Angel is they are calling these poppy seeds. Bright Angel is the formation. But Bright Angel Trail is, for me, a place in the Grand Canyon, so I have a hard time getting my head around this. And they really are not leopards. They're not poppies. So, but this is what the geologists do to keep themselves interested, I guess. But the reason why this is important is not only because they found iron and phosphate and a mineral that forms it, but they have found iron phosphate minerals that are formed on Earth very much frequently associated with biological sediments. And so vivianite is very much found in Earth where you have organic material rotting organic material, reduced organic material. Phosphate is very abundant, very much concentrated in soluble, accessible form in life, including you. And they found it in the presence of organic materials. And so if you look at their paper, they have something they call the G band, which is indicating that this has iron, phosphate, and organics together. And iron, of course, is essential for life. You use it not only for hemoglobin, which is because you're an animal and you have to have this circulating oxygen supply, but you also use it for all oxidation reduction reactions inside of your cells. There are processes called cytochromes, which contain iron, and iron is a very important part of almost everything that goes on in biology, all the way down to microbes. And of course, phosphate is everywhere. It's, of course, found in DNA and RNA, but it's found in ATP, which is adenosine triphosphate, which is the energy currency of your cell, and it's, again, tremendously concentrated in living systems. So very often when living systems die, and in fact, you can go onto eBay this evening if you like and buy yourself a clam, which is a fossil clam from, say, 20, 30 million years ago, which has vivianite crystals growing within it. Because after the clam met its unfortunate fate, the iron and the phosphorus got together to make the mineral, and they're brilliant green, translucent crystals, which are very pretty, and they have found them on Mars. Organics, phosphorus, and iron, three things. Spectacular.
Admittedly, I have been the unfortunate fate of numerous clams in my life. Now, as a chemist, though, what are the other pathways to create vivianite that doesn't involve biology, and why can they be ruled out in this work?
Right. No, exactly. Right. So the problem that you have with biosignatures in general is this problem of false positives. So let's just go say we go to Mars and we find an amino acid, perfectly good amino acid, glycine, or glutamate. You eat glutamate when you eat monosodium glutamate is a flavor additive in food, for example. So you find it there, you say, glutamate is found in Earth life, in Earth proteins, in Earth food additives, and so this is a sign of life. But then you go look at a meteorite, which coming in from a comet or some sort of non-biological substance that contains organic compounds, and you find glutamate there as well. So this is the so-called false positive problem. So your first question is, if you see vivianite, now you see vivianite all over the place on Earth associated with life, how do you know that there isn't some non-biological process, maybe something that occurs in meteorites, the same meteorites that are making the glutamate, right, non-biologically? How do you know that there isn't a non-biological source of vivianite for these materials? Now, the answer is there are some non-biological sources of vivianite. If your listeners ever get to the middle of Maine, a town called Newry, which I very much advise you to, you can go to a mineral museum in center of Maine, the middle of nowhere, where they have great tourmalines that they have mined gemstones from the local, what they're called pegmatites. This is a metamorphic rock, which I'll tell you a little bit more about in a minute. And they find vivianite in that rock. By the way, that museum, if you don't have any other reason to go there, the man who got rich mining tourmalines decided to spend his profits buying up meteorites. So they have one of the largest meteorites from Mars in that museum, roughly the size of my head. And they have a great, spectacular collection. The only thing wrong with it is in the middle of nowhere, so you have to drive maybe 3 hours away from Portland, Maine, to get to it. But back to the subject. So there is vivianite in those rocks that are coming from non-biological sources. The pegmatite that I referred to is a kind of rock formation that is formed deep underground with supercritical water, hot under pressure water, which will dissolve all sorts of things that normal water does not dissolve. And so there are tourmalines that are growing from that, which is what they mine the rock for. But there's also lithium phosphate minerals in fact, there's a lot of lithium minerals in here, which is one of the reasons why when we try to come up with a lithium source in the United States, they go to pegmatites in Maine or North Carolina, other places where they're found. So there are lithium iron phosphates, which are the sources of the iron phosphate, which is vivianite. And so these are high temperature. We're talking about several hundred degrees high pressure. The water has to be 300, 400 degrees centigrade, 800, 900 degrees Fahrenheit. So that water would not be liquid water, except that it is buried deep in the ground and under high pressure and therefore can't boil away. So those kinds of sources of vivianites are known. You can go through the geological literature and you can find examples of these in various places. So there is possible for vivianite to form without life. In fact, it's in principle possible whenever you have iron and whenever you have phosphate. We'll get to a little bit more detail on that in a minute. But the problem with this is that Jezero Crater, which is where the Bright Angel Formation is, it's the Mars Perseverance rover was sent there because it is an outflow of water from a crater in Mars that looks like it has a 3.5 to 3.8 billion year old surface, which has never been buried. It's never been put under rock, and certainly not enough rock that you can get supercritical water at high temperatures, 500 degrees centigrade, 1,000 degrees Fahrenheit, whatever your favorite measurement is. And that rock has never been buried. That rock has never had high temperatures. It's never had high pressures. So we don't know of any other low temperature way of forming vivianite except by getting biological iron and biological phosphorus eroded in some sense into that mixture. Now, keep in mind that the reason why biological is used in that sentence is because biological species concentrate phosphate from the background. And so that's means you only get iron phosphate to precipitate as these lovely green crystals if you have a lot of phosphate. And you only get a lot of phosphate if you don't have, well, you certainly do get it if you have life. But the question will be, if you don't have life, where does the phosphate go? Well, the answer is it goes into other kinds of rocks. In particular, it goes into calcium phosphate, which has a mineral which unfortunately has a bad name also, called apatite. It's not spelled Appetite, but Apatite, apatite, yes. It's from the Greek word appetite, to deceive, because it comes in many colors and shapes and so on. So it's very hard minerals for the early Greeks to identify. We now can identify it easily. But the point is, the fact that you have iron phosphate and not calcium phosphate implies that you did not have as much calcium around as you had iron around when the phosphate was free and available to be precipitated. And so that means that this, again, is looking for this is not just the precipitation of iron and phosphate, which happened to be there. It's the precipitation of iron and phosphate that was concentrated by something. And if it had been concentrated by something non-biological, it would have been precipitated by calcium, not by iron. Is that clear? Ask me anything.
Oh, no, keep going. It's perfectly clear.
Okay.
Although I will give you an observation. When I start hearing these words like phosphorus, iron, carbon, I start getting the chills thinking that's the building blocks, Anyway, continue.
No, those are the building blocks of life. And so Joel Hurwitz, who was the first author in this paper, was extremely, extremely, extremely cautious as they wrote this paper. And in my view, a tad more cautious than. So keep in mind, these people are not chemists like I am, and so they don't have necessarily the instinct. So, for example, what they do see, they see a small amount of an iron sulfide also. And of course, keep in mind that sulfide is sulfur, and sulfide is in biological systems reduced. In the bulk rocks, the sulfur is not reduced. It is oxidized. It is sulfate. And in fact, they see calcium sulfate in these sediments from 3.5 billion years ago. And so one of the questions is, where the hell does the sulfide come from? And so one thing that they say is that, well, maybe the organic material came from something else, not life. And then the organic material coming from not life somehow managed to reduce the sulfate to make the sulfide, not life. And and they write that such abiotic reactions are extremely slow at temperatures less than 150 to 200 degrees centigrade. Well, they are extremely slow in temperatures less than 1,000 degrees centigrade. In short, they're very slow because, among other things, thermodynamically, you just don't take carbon, organic material, and reduce sulfate with it. It just doesn't work. You can go try it yourself in your backyard if you want. So the point that we've made is, and that they make as well, but I just made to you with reference to this deposit pegmatites in Maine, you got to get burial to 5 kilometers, temperatures more than 150 degrees centigrade, actually much more. And there is no reason to believe that this sedimentary rock has ever been buried at all. In fact, it looks like it's you can still see rivulets of water running through the morphology of the rocks, the shapes of the rocks. It looks like this is a delta from an outflow from a lake that was bounded by Jezero Crater 3.5 billion years ago, and it has never been buried, period. In fact, they're dating it by looking at the impact craters, a little bit of meteorites here and there. And so this idea that, and I'm sure a referee made them put this into this paper in the detail that they did, but the alternative for a non-biological formation of vivianite in the presence of organics involving the reduction of sulfate by carbon simply isn't credible. Now, keep in mind that one of our problems is in science is there's no such thing as proof, right? Well, there's proof in mathematics, but in science, there's always the chemistry that you don't know about that could have created the materials that you are observing transparently. And so we always say, well, we'll talk about a preponderance of evidence or evidence beyond a reasonable doubt. These are terms that you hear in courtroom dramas. But certainly in terms of the preponderance of evidence, the fact that I can't think of a non-biological process to produce this means that the burden of proof now is on those who want to argue that this is not a biosignature, as opposed to those who. So the argument ends, right? The people who are arguing that this is a biosignature will have won it. Of course, then again, this has got to be examined from the perspective now of people trying to attack this as a biosignature.
Would you say within astrobiology, which both of us have been keenly interested in for a very long time now, and this seems to be the case to me, would you characterize this as the closest we've come to the discovery of life on another planet?
Yes.
Would you go so far as to say, well, I think one thing we can say, if you want to add something to that, this is the most interesting Mars rock we've ever seen. I think it might have.
Well, we've seen a lot of interesting Mars rocks. I mean, I thought Allen Hills was fairly interesting. I think at the end of the day, the sample was not what we wanted, and certainly the people at NASA who were clever enough to pick Jezero Crater to go to made the correct choice.
Oh, I don't think there's a question. Jezero Crater, well, you know, the Bright Angel Formation itself, you just look at it. That is a riverbed. It looks the part.
Yes.
And to be honest with you, I want to know, what do the other rocks have going on? Because there are thousands of them out there in that riverbed. But it's still, even 3.5 billion years later, it still looks like a dry riverbed.
It does.
The other thing is that in this evidence, as old as this is, 3.5 billion years, as old as this evidence, potential evidence for biology, that also is from a time where we have a extreme scarcity of rocks on Earth from that period.
That's right.
Very little. And we do have some evidence. Now, this is a weird question. If we had found that rock on Earth, say we found some deposit and we pull it up, would it meet the bar of evidence for biology on Earth? In other words, they would look at this and say, no, these circumstances, that's got to be the action of microbes. And we do that with things like the zircon crystals and all the stuff that, evidence for early life we have on Earth. If this rock had been from Earth and found on Earth, would it just simply be chalked up to life as the simplest explanation?
Yeah, well, that's a good question. I mean, the problem that you have, I don't know, have you ever been to Strelly Pool Church, these places in the Pilbara in Australia, and looked at the actual Buick Formation outcroppings that have the stromatolites from 3.46, 3.5 billion years. Have you been there and seen them in person?
Sadly, I have not. I have not yet actually been to Australia, unfortunately.
I would recommend if you get a chance to go there, and this is also to all of your listeners. So if you actually look at those stromatolites and you take someone along like Martin van Kranendonk, who is the Australian guy sort of in charge of guiding people to this place, you will see geophysics. You will see the movement of water percolating where you can see sand particles that have come up against the stromatolite and have not gone further. You can see the dynamic motion in the site. These are really very persuasive argument. The argument is very persuasive that these are biosignatures by context in great detail. And so the reason why this particular rock from Mars would not be immediately called life signature on Earth is just because we have so much better examples of life signatures on Earth from that date. But yes, I mean, there's no question that the sediments would be regarded as sedimentary rock, and then they have this word in the paper, which you'll see several times, called orthogenic, which means that you're making the minerals in those sediments, not metamorphically, not by burying them, not by doing other things. And yeah, this would be something that, again, the burden of proof would be on anybody who would want to say that it was not the result of a biological precipitation of some kind, or maybe more complicated than that. It's in the first place a biological concentration of phosphorus, biological concentration of iron, biological concentration of organics, which then died, and then you have the resulting mineralogy occurring from it. And this would be certainly the preponderance of evidence interpretation under this, geological dictum that every rock has a story.
Absolutely. And sometimes it tells us the story, sometimes it gets erased and melts and comes out of a volcano, which is interesting in and of itself, actually, to see rock form. But now with this, so basically it seems to me, and they actually say this in so many words, I'm paraphrasing, this is not a quote in the paper, that life is the simplest answer for this sample. It seems, now that you find all the problems with, any alternative chemistry. So where does it go from here? And, now that it's out there and all the scientists can try to start shooting it down, what are the chances that they'll be able to do it? And where does it go from here?
Well, a couple of things. First place, the simplest, you got to keep in mind, I'm not a big fan of Occam's razor, even though Jodie Foster made it the central part of that movie, or Carl Sagan made it the central part of that movie with Ann Druyan about contact. Basically, because what you think to be simple or complex is very much a statement about what you think is simple or complicated. So you have, of course, a background which lets you have certain expectations of things that are likely and things that are not likely. And if you had a different background, you would think differently. But never mind. There's the problem right now for the burden of proof. Remember, this is an argument. It'll go back and forth. Right now, we have a mechanism for forming this biologically. We do not have one for forming it non-biologically. So the burden is now on the people to come up with some non-biological approach. Second, we have relatively good understanding of how life would have emerged on Mars, maybe even better than on Earth, given the geological context. And so we have fundamentally put in place the predicate, right, that this is being concentrated. The organics, the phosphate, and the iron are all being concentrated by a biological system to give them the opportunity to form these minerals after the system dies. And so now your problem is you got to shoot down that too at some level, because one way of getting rid of the conclusion is to get rid of the predicate. So if you can say that Benner is crazy, that his model for how life or RNA life emerged on Mars is just stupid, then you get at least rid of the predicate. So now the burden would go back to the people who had to say, okay, if this is life, then tell me how it originated on Mars. But your next step, of course, is the one that you're not going to likely get, and that is the sample return. You would like to have that rock. Very much, I would like to have that rock back here on Earth, because then you could easily look at isotope ratios in the carbon, right? The carbon-12 and the carbon-13. Carbon, as your listeners probably know, comes in two isotopic forms. Carbon-12 has got 6 protons and 6 neutrons as its nucleus. Carbon-13 has 6 protons and therefore reacts the same, but 7 neutrons in the nucleus, so it's heavier. And we can talk about the signature of creating light carbon. The biological systems very often will have more carbon-12 than carbon-13 in their organic material. We would love to have that sample here on Earth to look at that carbon-12, carbon-13 signature. And if we had it on Earth, by the way, and you were trying to write your PhD dissertation saying that this is a biosignature, you would go back and make that measurement before next Tuesday. We don't have that sample back on Earth, and right now the sample return has become so complicated and so expensive that it doesn't look like we're going to get that sample back on Earth. The next thing that you would do is you would love to know, okay, so that's a good question. I can give you 12 or 13 other experiments off the top of my head. If I had that rock in my lab, that would settle the case one way or the other about biology. So now your next problem is, what are we going to do without sample return? And that's a complicated story, and I don't have a good answer for you on that. So that's where you're sitting. And then I'm sure you've seen part of the press conference. There were questions afterwards. A few of them were asked, and one of them was asked about the sample return mission. And Sean Duffy, who is the Secretary of Transportation, but he's also interim or administrator of NASA. I guess you can argue that NASA does transportation. Basically is constrained by a budget issue, and he is non-committal, but at least he did say yesterday that science is still going to be supported by NASA. And so we could go into the laboratory tomorrow and try to, with Earth reagents, we'll buy a little iron, we'll buy a little phosphate, we'll buy a little calcium, we'll buy a little sulfate, we'll buy a little organic material from our local supply house, and then try to simulate the formations of those structures in our laboratory under conditions that we think would mimic those. But that's all I can give you for now. And the question, of course, relates to the fact that the most important thing in science is money. Right? You got no bucks, no Buck Rogers, as they said in the movie The Right Stuff. You're going to have to get some talent paid to go back and do simulations on Earth. And then, of course, the rest of it is in the NASA next mission concept. We're sending missions to Europa. We're sending missions to Titan. Those were both mentioned at the press conference. But frankly, we have been very much frustrated by the hesitancy of NASA to send missions to look for extant life on Mars. And that's something I think would be the next thing that we would recommend.
Hear that, everybody? Write Congress and ask your representatives. And it's what you can do is a public outcry that says fund this,
Yep.
And because here's the sad thing. The Perseverance mission was designed, the sample didn't just get thrown away. It's in a container on the rover that is designed as a sample return. So you send something to go and pick this up, and it was designed for that. It was designed to be picked up. And it would seem like a total shame if the most important rock ever discovered in the solar system, maybe even better than Earth, just sits there unretrieved when it was designed to be retrieved, along with the other samples. There's other interesting samples in there too from other rocks. It's been doing these cores for, since it got there. And it would be a shame, I think.
Well, you can always ask the Chinese to pick it up. So
they might. They probably have a better chance of doing it.
But let me speak more broadly. So, one of the things that Elon Musk has taught us is that space is not just a public exercise. Now, you got to keep in mind that my father-in-law was a guidance engineer for the Apollo moon landing, so I'm a NASA family person. In the good old days, a substantial fraction of the gross national product was spent going to the moon, and that was something which is a public good, right? You can't provide, to the extent to which NASA does the Webb Space Telescope, it delivers to the public. It's sort of highbrow entertainment, right? It's sort of a public good. You have these wonderful pictures, you produce knowledge. Like any public good, you can't give it to one person without giving it to everybody. And so the only way to fund that is by having public activity. And so you should write your congressperson to talk about this. But then what Musk showed, and remember, Musk's Starlink, I mean, he makes more profit than the entire NASA budget, right? So, and if you look at a Steven Spielberg movie, I mean, Spielberg basically can't make a movie without an alien in it somewhere. So, this is more than, as one mentioned with Jurassic Park, they spent more money to make Jurassic Park than the National Science Foundation spent on dinosaur research, right? You make more movies, on Star Trek, Star Wars, and all the rest of it than the entire NASA budget. So there's an appetite for public use, but there's also the possibility of private missions right now. We have there's a company here in Texas called Gwin. It's an engineering firm in Austin, actually, which is where I'm visiting right now. But also, on Spotcheck and the Mars Agnostic Life Finding Association at Mars, these are private entities which are putting together now missions to go to Mars to do agnostic life finding or to do democratized, privatized, small level, maybe $10,000 each experiments. If you can get a ride on Musk's launcher for $80 million, which is, of course, a small fraction of what Apollo cost even before you start adjusting for inflation, you can get private missions to go to Mars to do various experiments. Now, you're not going to put down a rover, right, which will then wander over to the spot in Jezero Crater to pick up this sample. You're not necessarily going to do sample return. There's a big question about planetary protection, whether you can bring samples back and whether they present a risk. And I happen to think that they don't present much risk. Barry D. Gregorio, who is in this space as well, thinks that they present more of a risk. So there's a disagreement here. This is one of the reasons why the samples are not going to get returned anytime soon, because of the cost of protecting against planetary contamination. Now, I find that to be a weak argument because, frankly, I've got about 20 grams of Mars in my office right now. And of course, the museum that I mentioned in Maine has a couple kilograms, maybe 500 kilos of Mars come to Earth every year. A few more grams from NASA is not going to make any bigger of a risk in my view. But there's a disagreement on that. But back to the point. So yes, the next step is going to have to do something with getting that sample back as maybe the most important rock that we found, certainly in a long time. And, I don't actually see right now a clear path to do it, either by public activities or, unless we exclude China, or by private activities, until we get humans going there. So the interesting point about humans visiting Mars is, under the International Treaty on Space, if we send humans to Mars without having done a biological survey of the planet before we do that, and then the humans go there and discover evidence of life, we are not allowed under the Space Treaty to return them to Earth without showing that the life that they have been exposed to has no hazard on Earth, which is going to basically leave the astronauts stranded, or we would violate the International Space Treaty. But the point is that we desperately need to have robotic missions going to Mars now in anticipation of human arrival to do a biological survey of the surface. That still does not get that rock back from Jezero into my lab, which is what I really need. But the humans could bring it back.
Yeah, robot geologists are nice, but they can only do so much being robotic on the surface of Mars. They're explorers.
That's right.
You need it in the lab where you've got all the big expensive equipment that you can't launch. Let me ask you this. This is an off-the-wall question. If you own a pharmaceutical company, would going and looking at in situ life on Mars, do another labeled release and return samples, because we know they have money, would you do it, or would you say no?
No, I would do it. I mean, we have, of course, if you go to Agnostic Life Finding Organization, which is it goes under the abbreviation Alpha, ALFA, Mars.org, or you go to my blog, primordialscoop.org, one word, you will see what we would propose to do to look for extant life on Mars. One of the things that is not widely appreciated, and there's a historical reason for it, is that all three life detection experiments were positive for Viking in 1976. In fact, even the fourth experiment, which was a gas chromatography mass spectrometry experiment, which is recorded in textbooks as not having found organics on Mars, did find organics on Mars. What's very amusing, and I've written pieces on primordialscoop.org, which you can read, one of which is titled is How Does NASA Culture Get the Viking Results So Wrong? Is that you'll discover that when the guy, Klaus Beeman was his name, professor at MIT, saw methyl chloride being produced on Mars, they also saw freons on Mars. They had seen the freons when they tested the instrument in the flight to Mars. They had not seen methyl chloride in the flight to Mars. Beeman actually says in his original paper that the methyl chloride could be indigenous to Mars. We now know that methyl chloride, this is a man named Navarro Gonzalez, who unfortunately died of COVID a couple of years ago. But Rafael Navarro Gonzalez actually showed that methyl chloride is a byproduct of the oxidation of organic molecules in the presence of perchlorate. Klaus Beeman in 1976 did not think of perchlorate. He did think that there might be an oxidant in the surface of Mars that would burn the organics as he heated them up to get them into his instrument, but he only thought about nitrate. Every high school kid who's ever made gunpowder knows that organics and potassium nitrate makes gunpowder, and therefore they knew that you were burning the organics and would not see them with nitrate, but they did not think about perchlorate. And so because of that, Beeman says methyl chloride is possibly indigenous to Mars. But when he wrote his review article, this is the deadly thing. We tell students that you always look at the original literature. You never look at the review article. When Klaus wrote his review article, methyl chloride moved from being possibly indigenous to Mars to being a terrestrial contaminant. And then when Norm Horowitz wrote his review of the review, he said that all that Beeman had found was cleaning solvents because Horowitz, being a biologist, did not know the difference between methyl chloride and methyl dichloride, which is a cleaning solvent. Methyl chloride itself is a gas. It boils at minus 26 degrees centigrade. So when you follow this literature, the detection of organic molecules by Beeman became the failure to detect organic molecules. And that Gil Levin's label release experiment, which you alluded to, your listeners may not know that he fed radioactive food, carbon-14 food, which is a radioactive isotope of carbon, to the Martian surface and saw the release of radioactive carbon dioxide very quickly. Okay, and Gil died a couple years ago at age 97, still saying that he had found signs of biosignatures, and I suspect that he was right. That the problem was that they assumed that there was some sort of non-organic oxidant that was able to produce that result, and we still do not know about any oxidant that would produce those results. Richard Quinn has an example. Maybe bleach was produced, and there's a good reason to believe that doesn't meet any burden of proof. But then, and then Norm Horowitz, even Norm understood that there was a problem. Norm had looked for photosynthesis. They had put radioactive carbon dioxide above Mars and saw the fixation of organics. If you read Norm Horowitz's experiment paper, he says, we've hypothesized that there is a very strong oxidant on the Martian surface which burned Gil Levin's food, made radioactive carbon dioxide. Now, that's incompatible with my experiment where we saw the fixation of organic carbon in the surface of Mars. But then Horowitz writes the phrase, and I'm not more or less quoting him, experiments are ongoing to try to resolve this anomaly, and we're sure that when they're completed, we'll have figured this out. Now, the experiments have never figured this out, and we teach the students now, in addition to go back and read the original literature, there's a second law of science, which is never trust the results of an experiment that has not been run. But Horowitz basically makes the presumption that when the experiment is run, we'll have figured this out. And I have written an article, a book chapter actually, for Carol Cleland, who is a professor of philosophy was an astrobiology philosopher at the University of Colorado. She actually operates under the assumption that when scientists see anomalous data that contradicts their theories, they go back and re-examine their theories. And scientists generally don't do that. What we normally do is try to dismiss the anomalous data, attribute it to a broken machine or something we don't understand, or we ignore it. And that's exactly what happened with all three life detection experiments. All three of them are actually consistent with a form of life on Mars that is a bacterium. It's an autotroph. It does photosynthesis. It respires with oxygen that it stores for overnight metabolism. And that's exactly the kind of lifestyle that you would expect for an organism living in that environment. And it's fortunate that bacteria autotrophs respiring with stored oxygen for overnight metabolism is an acronym which spells out BARSOOM,
Yes, burrows. Yes.
BARSOOM, bacteria autotrophs respiring with stored oxygen for overnight metabolism, which for those of your readers who don't know, that the author of King Kong, Edgar Rice Burroughs, also wrote something called John Carter, The Princess of Mars, where the Martians called their planet Barsoom. Coincidence? I think not.
Yeah, well, there's enough of a corpus of from the label release experiment to now with the new Sapphire Canyon sample. There's just been every few years some hint of Mars life, past and present, perhaps. And we could talk about the methane blooms and just all sorts of mysterious things that happen in that
Yes.
at that planet. But let me ask you this and frame it and go into any of those you like. And by the way, I didn't know Gil Levin, but I knew Patricia and Straat, who was and I
Oh, yeah. I never met her. I knew Gil well, but never met Patricia.
sadly I was the last interview she ever did before she passed away.
Well, I own her book, So Mars or From
Oh
Mars.
yeah, that's From Mars with Love, I believe. Yes, which is actually an interesting book because she had a great interest when she was younger in equestrianism. She's a horse rider, and it's an interesting book. But she maintained that she could not rule out life up until the very end. She just couldn't rule it out. She's like, I'm a scientist. She was at Johns Hopkins at the time, and I was like, and she was like, I cannot rule it out, and I wish someone would do it effectively and show me. So it's very interesting.
No, again, no, look, by the preponderance of evidence, if you make your arguments conform in logic to something that Aristotle would recognize as logical, right? If you accept the data as it's reported, not as it's reviewed, the preponderance of evidence said that Viking discovered a microbe that was a bacterium which had stored oxygen. They saw that stored oxygen released. They saw autotrophy. They saw the fixation of carbon from the atmosphere, and they saw metabolism. They saw everything that they set out in those experiments as originally designed. They found what those experiments said was going to be taken as biological signatures. They threw it away, all for reasons that do not survive, meaning an experiment that was not designed to be live detection, the gas chromatography mass spec from Klaus Biemann. That experiment was not sensitive to detect life on the Atacama Desert, for example. But Jerry Soffin, who I knew, maybe you met him, he's no longer living. He was the director of the Mars mission, and he said, that's the ball game. No organics, no life. And that poisoned the discussion. It prevented the back and forth. It's been published in Science magazine. I've had a back and forth now with the editors of Science, including Holden Thorpe. They retracted the arsenic DNA paper, but the point is that I tell them, like, that's nothing. I mean, the arsenic DNA paper was managed by normal scientific process. It did no damage. It's a great story of the success of the scientific method. But the report in Science where they moved methyl chloride from a Martian organic into a terrestrial contaminant that poisoned. And for 20 years, there was no mission sent to Mars. The only reason why Mars exploration resumed was because of the Allen Hill meteorite in 1996, where they thought that they had they thought they had seen some microbial fossils. But the point is that I'm trying to get Science to put a editorial on the 50th anniversary of the launch to Mars, a statement about how that process corrupted the whole outlook of Mars. And by the way, we can still go back to a 2022 report of Vicki Meadows and Heather Graham. Vicki is a well-known astronomer at University of Washington. Heather Graham is at Goddard. They got a committee together to come up with a consensus view of how we should treat biosignatures. And they, in their opening paragraph, they spend a whole paragraph. In fact, they have 3 paragraphs. Each one of them is wrong, and as we would say, even the words "and" "the" in the paragraphs are wrong. They basically do not understand the Viking results. I don't know if you know Brian Dobbs. He's one of your competing podcasters. He makes some stuff for Netcast and people. But the bottom line is that he basically says as well, the astrobiology community does not know the primary data that go into that came out of the Viking mission that go into our analysis and our mission design. And the result was the mission designs for 50 years now, a half a century, have been corrupted by people who don't read the original literature, don't do Aristotelian logic, and assume the outcome of experiments that they don't bother to run.
If you were given carte blanche money to send a 2025, which would probably be about 2032 or something like that,
right,
version of the labeled release experiment and the other experiments that were on the Viking landers, which, by the way, those experiments were on both landers, right? They both saw the same thing.
That's right.
So whatever this is, it's widespread.
It's
on
reproducible.
Mars. Yes. So that was another. It's reproducible. That is another thing that was of great interest, and they thought that through. Now I have a dual question on this. If you could send one now, what would you do differently from the Viking missions, and specifically, would you try to devise an experiment that could spot chirality?
Yeah, absolutely. Well, that was where I was going to go. But there are 2 points. First place, NIAC. I mean, NASA is aware of this. I mean, NASA is, of course, NASA is not, I mean, NASA is a building, it's an administrator, it's a logo, it's got, but of course, NASA really is responsive to the community. So our goal here is we have to get the community to go along with this. And we're making progress. So we have designed an agnostic life-finding instrument, which you can read about on primordialscoop.org, but it's also been published in the peer-reviewed literature, which is looking for the chemicals that are required to create Darwinian evolution, not chemicals that are the products of Darwinian evolution. And the reason for that is, again, this false positive problem. And almost all the chemicals that we know on Earth that are the products of Darwinian systems, like you and me, can also be made abiologically. But the chemicals that are necessary to support Darwinian evolution require Darwinian evolution. And so these are what are called polyelectrolytes. I can perhaps at a different time and place give you the details. But we have built a machine. It's actually in technical readiness level 5. It's with the supports of the NASA Innovative Advanced Concept NIAC program. And this has been built. It's sitting in our laboratory. We're now trying to get phase 2 funds to go get it to technical readiness level 7 or 8. And then our hope is to present it to Elon Musk or the Chinese National Space Agency, whoever is interested in giving it a ride to Mars. As a fait accompli, we know how we would detect this life on Mars unambiguously without false positives. And so that's what I would do. Now, yes, I mean, to improve on the Viking, this is in addition to what Viking did, because people did not have access to, people did not know where there was water. This would be something that would look at large volumes of near surface water. This would be water that would be mined by SpaceX or NASA or the Chinese National Space Agency as a resource for propellant synthesis, for example, for the return home, as a resource for the astronauts. So there's a larger sample volume, and this is ice that's near the surface of Mars. It would certainly be contaminated on Earth by microbes if it were on Earth. And so that's what we would do first. But yes, to improve the Gill-Levin experiment, this is not our idea. I mean, Gill had this idea. You would go look for left-handed food versus right-handed food and try to see a difference between these two. And Gill actually designed that experiment originally to fly that way. They did not have the budget for it. And so it was not done. But certainly a difference in left-handed foods' rate of oxidation versus right-handed foods' rate of oxidation would be something that you would take as a very strong biosignature, not terribly susceptible to false positives.
And if it comes back the opposite chirality of Earth life, you got a good indicator that it's truly a second abiogenesis. However, with the findings of this, where we're looking at something that looks like something we know that Earth life does in the sample, that brings up an interesting term, and I will say it here: convergent abiogenesis, in that there are certain commonalities forced by chemistry to dictate what microbial life can do. Do you agree with that term and that statement?
Oh, I love the term. I mean, the convergence. Keep in mind that I've used the phrase already, privileged chemistry. That is, it's this chemistry that could not have happened. So if you have a carbon dioxide atmosphere with water and nitrogen in it, and you have it bombarded by solar radiation and, various other things, you cannot not make formaldehyde. One carbon, two hydrogens, one oxygen. It's the most primitive carbohydrate. And by the way, you could not have not made two carbon sugars as well. And in the presence of rocks that contain, among other things, boron as an element, you cannot not have made five carbon sugar ribose. Okay, so this is the kind of privileged chemistry where you're not really talking about convergence, right? What you're saying is that built into the reactivity of carbon, hydrogen, nitrogen, oxygen, boron, phosphorus, or whatever, intrinsic to that chemistry is the propensity to make ribose, the R in RNA. So there's this idea of convergence. It's almost sort of what we would call predetermination. So in some sense, you can find a carnivore in Tasmania, carnivore in Africa. They're not related by common ancestry as carnivores, but they have the same kind of teeth, and there is a convergence for function. But what we're talking about here is a little lower level. We're saying that the molecules themselves, the intrinsic reactivity of the atoms and their combinations in molecules is such that you get informational biopolymers, which are then able to support Darwinian evolution. So there you go. So, and this is not true just on Mars and Earth, but it would also have been true on Venus and every other rocky planet in the galaxy. And the problem with Venus is going to be that the evolution of that planet was to an acidic environment, still a lot of liquid. The evolution of Mars was to a rather dry environment. The evolution of Earth, of course, was to an oxidizing environment, partly because of the life that put this poisonous dioxygen into our atmosphere, which, of course, life learned to use.
Now, this is my second to last question for you. If you have a microbe, an active microbe that can survive on the surface of Mars, in the upper soil anyway, like with the labeled release experiments, that is a very hardy microbe. It's gonna be using UV. And
Yes.
microbes, they can eat chemicals. That's what they do. And that doesn't really necessarily involve chirality. It just involves elements and obtaining those elements.
Yep.
Is it possible that if we go and we dump some astronauts on the surface of Mars, whether it's the US, China, or SpaceX, whoever does it first, without doing a life-finding experiment like what you've designed, could that endanger the mission? And is it dangerous to bring a fresh sample back? Now, I don't think so, because like you, I have a piece of Mars myself. I have a sample of Nakla, and it doesn't kill me. I'm actually more suspiciously eyeing the piece of trinitite I have, and the uranium glass collection. But do you think if you're actually going there, because it doesn't require any sort of panspermia if you're standing on the surface of Mars, it seems to me we need to know if there is a danger to the astronauts before we send them. Therefore, go and do some direct life-finding experiments. I think that's prudent. What do you think? And do you think a Martian microbe can generalize so much living on a dying planet that it can eat almost anything?
Well, that's a good question. I mean, keep in mind that parasites very much co-evolve with their hosts, and that's true for viruses in particular. So if the virus is not compatible with you and your metabolism and your chemistry, it can't eat you. It does not find you tasty. So parasites, and so a lion has to eat something that's close to being, homologous to a lion. And when I have my group over parties, I will put an evolutionary tree above each of the dishes that we are serving for the dinner to explain how closely you are related to what you're eating. I'm not encouraging cannibalism here, but the bottom line is that yes, there's a species barrier. Now, that doesn't mean you can't compete at a lower level for resources, and so that's the second point. Let me go back to the first point that you made. And of course, it is true that you very much need, if you're a microbe living on the surface of Mars where you have access to solar radiation, you need to be filtering it. By the way, that's also true on Earth. So you have carotenoids on Earth, and these are the colors of the leaves of the maple tree after you've removed the green chlorophyll for the winter. But so you can't live out in the solar radiation on Earth, even filtered, without having some ability to filter out the harder part of the UV. I mean, I'm looking at coccolithophores, which are the models on Earth, which are little microbes that have themselves inside of a rock. They precipitate minerals around the surface is what I would do to try to shield myself from the harsh part of the spectrum so I could use the less harsh part of the spectrum. But yes, you do need to filter. The organism would have to protect itself, just like organisms on Earth have to protect themselves from the nuclear hydrothermal reaction that's not hydrothermal, but hydrogen fusion reaction that's going on 90 million miles from you. But yeah, but no, I am absolutely for both forward contamination and reverse contamination regions, desperately trying to get somebody to do an evaluation of the biosphere on Mars before anybody thinks of sending foot there. The only advantage is that, Elon Musk is saying he's going to set his foot on Mars very early, and he's not, right? He's a publicist as well as a extremely talented engineer. The Chinese are going to say they're going to send people to Mars before they actually can for the same reason. And so we do have a couple years, but we don't have a couple years to wait to get started. We have to get started today to start getting things built to send to Mars robotically, to do an assessment of that surface and its biological status before we send people to Mars. And that's a full stop.
Now, my last question is related, but it goes back to our first interview, and that's regarding RNA generation and volcanic gases. Sure looks like what you found regarding that versus, with Earth, Mars had all that too.
Yes.
So it looks like Mars could have, probably not now, but it could have at one point when it had more of an atmosphere. It could have done the same thing, and there could have been RNA floating around everywhere. Give us an update on your work with RNA generation and getting that in classrooms, because it seems like a simple experiment. And
Exactly.
has that been repeated? Has some other team done the same thing with the volcanic gases? And how does that relate to the possibility of life on Mars? Because my personal view is that it sure looks like abiogenesis. We almost overcooked the turkey with it. We say, oh, this must be hard, and they did that with RNA. You remember the famous radioactive beach hypothesis?
Yes.
Because people were thinking in terms, this must be really hard. But you showed that it's actually really simple, and you get a lot of RNA out of that process, which means eventually you're going to get something that can be useful. It's got some structure that's just right to start the process going. And you have other researchers like David Deamer, which found that protocells can come out of a hot spring. Well, what's near a hot spring? It's volcanic and geothermal. What's nearby? Volcanic gases usually,
Absolutely.
which I think you did that work in Kamchatka. So what's your view on that? Give us an update on the work with DNA.
Actually, that was Armin Malkajanian, who was, I don't want to take credit for his work in Kamchatka. I've actually never been to Kamchatka, which of course only because it was one of the territories in a Risk game that you were playing when you were a child. But yes, I was Armin Malkajanian, who is of course a good friend. But yeah, that's a lot of to unpack in your last question. So first, there is a paper in Proceedings of the National Academy of Sciences, which we have just sent back a couple days ago, the final revisions in response to review. So perhaps that will come out. And yes, that work has been reproduced now many, many times with many, many samples of basalt from many, many places. And But yes, when I use the word privileged chemistry, what I mean is that this is chemistry that could not have happened. And, so much of prebiotic chemistry is, and people complain about this all the time, including creationist scientists like my good friend Jim Tour Rice, who will go back and say that most of prebiotic chemistry is chemistry where you buy a pure reagent from a supply house, you run a reaction, you discover it contains 2% of a compound that has some biological purpose. You say, ha, we've solved the problem of the origin of life. You publish it, and nobody bothers to read the paper except the news reports. And the news reports are all hype it. I mean, what we certainly have is in a Martian basalt environment, very much like what you find on the modern surface of Mars, but also like what you find in today's Iceland, but also what you found widespread on Earth. Making RNA appears to be at this point privileged. It appears to be a compound that could you not have been formed. Now, the point is the RNA is 100 nucleotides, 200 nucleotides long. There are people like Phil Holliger at Cambridge University who show that's long enough to have replicating RNA molecules. We're concerned that among that would be also RNA molecules that catalyze the destruction of RNA. And so the question is, if making RNA is a privileged chemistry that could not have happened on Mars, that's fine. Now the question has shifted. Can we find in those random sequence RNA molecules homochirality, which you mentioned a moment ago, which we think is important? We don't have the answer to that question yet. And second, in that collection of RNA molecules would the number of molecules, the kinds of RNA molecules that are constructive, that make more RNA, dominate those RNA molecules that are destructive and destroy RNA? And that's a very interesting question, which we don't have to go to Mars to answer. That is something we can answer in our own laboratories on Earth by studies of it. So does that answer your question close enough? And we'll have to talk later when that paper gets published.
Yes, absolutely. And I do want to say this, that I have a dual hope. So, I'm half a century old, and I have only one hope, because I don't think we stand a huge chance of discovering intelligent alien life while I'm still here.
Yeah.
But with the microbes, we have a good chance by exploring the solar system, but also the laboratory, because, out could pop, the Miller-Urey experiments and things like that. Out could pop a microbe from the test tube, and we understand abiogenesis that way. And if it turns out that it's easy to do it in the lab and produce a microbe from abiotic means, that must mean, if it's easy, it must mean that this universe at least teems with microbial life. And I would be a happy man just knowing that, because I could say, yeah, we're not alone in that, in biology. And I think that what you've demonstrated is that we live in an RNA universe where the generation, the abiotic generation of RNA happens. It just happens. It's a chemical out there, just like tholins and any other organic chemistry. And I love that.
Me too.
All right, Dr. Penner, thank you for sitting with me again today. And I look forward to further papers. It's always fun. It's always fun.
Okay, have a good evening.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.